Let's close this. And this. Okay. Last class we talked about Markov properties and Markov models. And then at the end, we said, okay, let's go one step forward. We said, if there is decision making when there is uncertainty, we introduce Markov decision process. We have agent, and we need to find policy, and so many new words we learned last class. But today we want to move another dimension higher, actually. Actually, no, we're just going to change time to frequency. We're not going to add another dimension, but we're just going to look at the problem in another dimension. That's maybe better explanation. We always scared of frequency. I always scared. Anytime the frequency come, I say, oh, that's for electrical engineering people. That they always want to say, oh, we know some stuff more than you guys. We know frequency domain. I was electrical engineer too, but I always scared of frequencies. But sometimes frequency, or look at the problem in frequency domain is, I can't say fun, but it's easier to see characteristic of the system in frequency domain. The main thing is when you look at the signal, like a noise, for example, if you look at the white noise, it's all noise. You can't get anything from it. It's so, especially if it's different, what they call it, visualization of that is so mess. You are not able to understand what is going on there. But if you take that and change to frequency domain, get, for example, Fourier transform, and take out the power spectral density, you see, oh, it's going to be understandable now. It's like you can see the power of that signal is concentrated in some specific frequencies. That's very interesting. And sometimes you can summarize lots of data in just a couple of numbers. Like if you are doing voice recognition, this is one of the methods of detecting voice. See, it was my undergrad project, my graduation. We had a project to graduate for even undergrad. And my thesis, if you call it thesis, was about that. I did with actually fast Fourier transform. I tried to do voice recognition. We did it, but it was very complicated. Anyway, what we did was we did some normalization in the voice, and then got kind of frequency, power spectral density in general. We got power spectral density, and we understood, okay, this word, we did it for words. This word has some actually concentration of power in these frequencies, and with this way we could summarize words with some numbers. Instead of having lots of numbers, when we digitize it, you're going to have it like 10 numbers or 5 numbers. And it was easier to detect. But right now with actually like deep neural network, that's going to be much easier. Okay, so that's what we want to talk about today. We want to look at random process in frequency. That's for topic today to talk. So, what else we're going to talk today? Let's see. We're going to talk about how look at random process in frequency. We're going to look at that. How we can go to the frequency domain, we can do a Fourier transform. And we're going to see how actually autocorrelation related to power spectral density, we call it S of F is frequency. So we want to see what is relationship between autocorrelation. Autocorrelation was R of tau. Tau is a lag, like T, like delta T. How we are changing in time, that's a lag. We want to see what is relationship between autocorrelation and actually power spectral density. What else we're going to see? We're going to see also different type of processes, how this power spectral density is different with different processes, like for example, for white noise, for a low pass filter, for example, sinus or cosine processes, how that change. So see different type of processes. Shape in frequency domain. What else? We're also gonna go for filtering a little bit. Filtering affects PSD or power spectral density. Because processes, if we look at processes as a signal transformation that was function in real world and it in discrete world was matrix transformation, in signal become filter transformation. If you want to transform a signal to something, you just need to use a filter. You need to make a filter and then I use that filter to transfer that actually signal based off that filter. We're going to talk about that too, how power spectral density can help that. Can we just use power spectral density and multiply, for example, power spectral density by that filter characteristic? Yes, we're going to see that. So this is what we're going to do today. So hopefully end of the class you can see relationship between processes and power spectral density and how we can do that. However, in following week also we're going to go more deeper in frequency domain. We're going to see more about that, especially we're going to go for linear time invariant systems and tell you, for example, Markov model or in Markov model or any linear time invariant systems, we can find the transformation matrices using power spectral density. Power spectral density give you transfer function, kind of transfer function. It's very amazing application of that. So even in Kalman filter, that the matrix F can be computed based off power spectral density. We're going to see that next class. Is very amazing how this frequency and time domain are related together. Okay, let's get started. First, frequency domain of random processes. So the random processes are not just in time. So what we did before, we said, okay, we have a random variable. We kind of evolve that in time, and that becomes random process. And it can have so many visualization of that, and that's random process. But what about instead of time, we look at this, because it's so mess, you can't get information from that mess, you know. But if you transfer that to the frequency domain, you can get something meaningful. If you change it to the frequency domain, it should be like this. Or, I don't know, even nicer, like just some days, for example. And that's nicer to understand the system, understand it, or get meaning out of it, instead of look at that signal that sometimes is all noise and mess. Is easier to understand that in frequency domain. And that's what we want to talk about. So the random process can study it in frequency domain as well. So this is what we want to say. In time domain, we already saw that how signal change over time. We talk about mean and autocorrelation. And with frequency domain, we also can have that. We're going to have something called power spectral density. We're going to see how power of these frequencies, because this signal has power. Like this, for example, has power. This has lower power. So this power of signal can actually concentrated in some specific frequencies or in some band of frequencies. So that's what we want to talk about, and that's called frequency domain of random processes. So the frequency domain helps us identify which frequency component dominate the process. That's important, showing which part is more power. Because not always all the frequencies have same power. If there is, that process is white process. The white process is like white light, has same frequencies of like all frequencies or all colors, for example. For example, white process is flat, and because it has equal power for all frequencies, which sometimes like or for example, low pass filter, you also have low pass filter. In low pass filter, most of frequencies concentrated in lower frequency, like you have here, something like that. It's like discount factor that we talked about. We said, okay, we have discount factor and it's less than 1. And when we are going in time, we put them, we power that by time, and this becomes this low pass filter actually created by this too. In low pass filter, to create this signal, you are using sigma multiply with a constant that is changing by k if it's discrete time. And that becomes low pass. This is however, is magnitude of that, or maybe it's a square. I'm not sure. We're going to see that somewhere in this. So this is going to make low pass. That this part is exactly like that discount factor. Anybody remember about discount factor? Can you tell me what was that last class? What that means? Yes?
It gets smaller as your time goes on. As time goes on, it gets smaller.
It's smaller and smaller. So it means we give more value to closest, for example, rewards, to last reward. If you want to give me $10 now, I like that compared to give it $100 1 year from now. That means discount factor. So discount factor is actually like that. When you are adding these rewards together, you give to later device or far later device less value with multiplying with that gamma power t. And t is, or t or k, whatever, t is time and k is also time slice, same way. And low pass filter is kind of doing that too, you know. So anyway, the low pass filter in the frequency domain is like that. So the power spectral density concentrated in a frequencies, lower frequencies. Okay, example, white noise is a flat spectrum, equal power everywhere. So the white noise is actually it was sigma 2. I always Dirac delta. This is also sigma 2 kind of. I'm not sure. Anyway, this Dirac delta is infinity if t is 0. If t is not 0, is 0. So this is meaning of this Dirac delta. So if we get if we get because we need to get Fourier transform of this to okay, maybe I'm going too fast. I need to first explain that and then talk about it. Anyway, if we do Fourier transform of white noise, it's gonna be just a constant value. You're gonna see that next slide. So that's why the white noise has a flat spectrum. So the flat spectrum, it means has same energy, the same power for all frequencies. So this is a white noise. For low pass colored noise, most of the power is concentrated at lower frequencies. For high pass filter, concentrated at higher frequencies. We also have periodic signals. Periodic signals like cosine and sine, they have a spike. They have a spike for those frequencies. For those, what omega means? Omega is angular frequency. I forgot the word. The angular frequency for example, however, in Fourier transform, actually the Fourier is amazing. We're going to talk about Fourier transform and Fourier series as well. But Fourier said we can actually find any function with combination of sine and cosine. This is what is his idea. And so sine and cosine are those spikes, because sine and cosine making the frequencies, those spikes, those periodic signals. So anyway, periodic signals can be summarized by one or multiple spike. This is what actually we're going to see in Fourier transform. When I'm talking about periodic, it means it's repeat. For example, this part is all repeating. Or maybe if you are combining multiple sine and cosine, it's not always, it should be like this repeating. I don't know. For example, this is repeating. This is repeating all the time. This kind of signals called periodic signals. The periodic signal can be just be multiple sine and cosine that add together. If you add them together, you're going to make a periodic signal. And the interesting part is when you are transferred from this domain to what that's called? When you are moving from, for example, this is, imagine this is time, and this is power. You can, if this is periodic, this is not related to the class. I just want to say this was one of the projects that I work on. So the shape of target, like not any, it needs to be convex. If you put a shape of the convex target, if you transfer, just instead of have t and power, have theta and rho, for example, you can make a like 2D shape because it's repeating, because that is repeating that shape, and you can model change of this shape using that too. That's very interesting topic. So anyway, I want to say how amazing is changing from frequency to time, and how many applications you can find in that, and sometimes becomes so simpler. So here is one dimension, but you made it, you modeled a two-dimensional picture. But with transferring to actually, I don't know, it's called homogeneous space. I'm not sure about that. Okay, let's go forward. So that is frequency domain of random process. So in general, we can actually model a random process using frequency domain to see what is the distribution of the power across that domain, across the frequencies. How we can transfer from time to frequency. So the general way is a Fourier transform. The Fourier transform is a method that you can use for transferring to frequency domain. So the Fourier is a French mathematician, Joseph Fourier, 1768, and he actually mentioned that you can model any periodic function by adding or summing sine and cosine. So it means any function, however, need to be periodic, x of t can be written as one term, like it's called a DC term, a0 plus plus sigma n is 1 to infinity an cosine cosine 2p and t periodic. T is a period. T is time, plus bn sine 2p and t, again capital T. So it means any periodic function x can be written as sum of some cosine and sine, some constant variables, some constants, not variables, some coefficients, a n and b n and a 0. This is something that Fourier mentioned. So in that time, and t, the capital T is a period because it's periodic. So it means that this function needs to be repeated in this period. However, this is if you go to imaginary space, this can be written like that as well. Because cos of theta plus j sine of theta is equal to e power j theta. So this is the base of this. We also can write that Cn, for example, ej2p n dt minus infinity to infinity. So this is another way to show Fourier transform or Fourier series. Sorry, this is not this is series of sine and cosine. So sine and cosine in imaginary space can be a right exponential. That's very interesting. You can see the relationship between exponential and sine and cosine. Okay, you don't need to go more deep in that, but we just need to know the characteristic of frequency domain a little bit. So like what? So the autocorrelation, okay, let's clean up this. First, if the autocorrelation function of x is r, and the process is white sense stationary, we can write, I said that there is a relationship between autocorrelation and power spectral density. And what is that correlation? Fourier transform. So between power spectral density and power spectral density of f and autocorrelation is Fourier transform relationship. What that means, it means if you get Fourier transform from autocorrelation, you're going to get power spectral density, and if you get inverse Fourier transform of power spectral density, you're going to get autocorrelation. So that relationship is very interesting. So first, Wiener and Khinchin found this relationship, and that's that formula named based with their name, Wiener, Khinchin or Khinchin, theorem. So, and this is the Fourier transform of our the Fourier transform of autocorrelation. Okay, so what that said, it said for each frequency, this gives us a value, a number. For each frequency, if you put autocorrelation function here and compute this integral, the result gonna be one number. For different frequencies, you might get different numbers. Some of them might be 0. It depends the process. If the process, for example, is white process, this gonna be different. Let's do it for white process. White process was, yes, the white process, as I mentioned in the last slide, autocorrelation of white process or of white process is sigma sigma is the power, and the Dirac delta, I think delta is written like this anyway, delta function of t, okay, and when we put that in this integral, the power spectral density, power spectral density is gonna be minus infinity to infinity. This sigma gonna get out because it's just a number, and this Dirac delta t and e power minus j2pf power, this is gonna get changed to tau. E of tau. So based off definition, what was definition of this Dirac delta was if t is 0, is 1, is infinity, sorry, and if it's cross infinity, and if it's not 0, is 0. So it means everywhere is 0, and just in t is equal 0 is not 0, and t is equal 0 make this part 0. So anything power 0 is 1, and so the integral in general gonna be 1, and this gonna be sigma 2. So it means power spectral density of white noise is just a number. It's just a power, sigma 2, sigma squared. So that's why for white noise, the power spectral density is just the power of the signal, because white noise still has a power, and that power is the sigma, but it's a constant. So I have the picture of that. It's something like this. It's all equal. It's not for all frequencies has like a similar distribution of power around all the frequencies. Okay, so this is how we compute power spectral density. So the power spectral density coming from Fourier transform of autocorrelation. Okay, so let's go to next part. This means that power spectral density is simply Fourier transform. So, okay, so we know that. Let's go one more slide. Power spectral density. So power spectral density, this is definition of power spectral density, is actually Fourier transform of autocorrelation, and this is autocorrelation in a continuous form, and PST is Fourier transform of autocorrelation. In discrete time, this sigma, this omega is changing to e power jw in a discrete form, because e power jw, we're going to see that later in the class, that is going to specify one point in a unit circle. EJW is just one point here. This is W, angular frequency. And nothing else. The rest is changing. Tau become K, and this is for discrete time. Interpretation, S omega is average power at frequency omega. So this is average because it's add them up, add them up, so this become average. And a unit of this is power per radian, per cycle, and it's continuous. Okay, what else I have? Oh, example for white that I already did that.